Let's get started. So this week we are talking about control and learning to control systems, specifically systems represented with MDPs. And we were talking about the challenges in doing that. And one of the challenges that came up was exploration. So this is quite pertinent when you have a system that you're interacting with and you're following a single trajectory. So you can't just like fly to places. So if you imagine that robot's interacting with a bird, it can do things little by little. It cannot just like imagine that, oh, I wish I was in this other room, and then it flies there. It has to get there if it needs to learn about that other place. So at the heart of this problem is the exploration problem. And last time I showed at the end this video that we should be reviewing first, which is of what happens in this problem where you have this cart pole swing up problem. Basically, you have a cart, you're pushing it left and right, a rod is attached to it in a flexible way. It can spin from the downward position to the upward position. Your only control is pushing the cart left or right with some unit force. And this is all the control that you have. And the reward is going to tell you, you are rewarded if the pole is in the upright position and the cart is kind of not leaving the beam or the platform. And so here in this video, we can look at what happens if you run some reinforcement learning algorithm with epsilon greedy. After a certain number of episodes, you see what the policy is going to be. So first it was 100 episodes, then 500 episodes, 1,000 episodes, and this is for the epsilon greedy algorithm. And it kind of like learned to freeze. Maybe there was some cost for doing things, and then it decided that it's better to just like stay in place. Whereas if you take this other exploration strategy, which is an instance of this optimistic exploration strategy, then you see that it's performing pretty well. And after 1,000 episodes, it learns how to swing up this pole and then stabilize it in the upright position. All right. Any questions about it? Yeah.
Doesn't like get rid of like the unhelpful actions it has taken.
Yeah, in a way, the epsilon greedy, and we're gonna have some examples to go through, not really the cart pole example, but a simple example where we can understand what's happening with epsilon greedy here. So in a way, in epsilon greedy, what is the strategy? You learn a policy which seems to be the best, and then you add little noise to the actions. So you can imagine that in this cart pole, what is happening is that there is not much reward that you can find if the pole is not in the upright position. Maybe you're penalized for every step or every action. Like if you have some input, it's energy, maybe you're penalized for that. And so it kind of at the beginning, maybe it learns, or like it just I don't know. It tries to do things because of the random noise, but it doesn't really have any systematic plan of exploring the whole state space. So in this case, the state space would be like, where is the cart? What is the speed of it? Like, does it go left? Does it go right? At what speed? And the angle of the pole and the angular velocity of the pole. This would describe the state of the system. And it's a 4-dimensional cube. And with epsilon greedy, it explored a little part of the state space. And it kind of tries to do things there, but it doesn't really have a plan of, escaping that. Does it make sense? All right, so actually what I wanted to do is to go through a simple example that illustrates what can go wrong with epsilon greedy. And the simple example is hopefully also going to help us to understand what these other strategies, these optimistic strategies, are doing in situations like this. Okay. So there's a plan. So this is the epsilon greedy versus optimism in the face of uncertainty. Playoff. And the problem that comes to mind is the winter. We don't like to go ski. So skiing. You have a mountain, and the chairlift goes up here. You start here on the top of the mountain. That's a skier. It's kind of a boxy. It's a robot skier. It's my new project to build these robot skiers. And it wants to find the most fun place on the mountain. And the mountain is very steep. So if it's at some position on the mountain, then it can go down. And it can go down, but a little bit to the left or a little bit to the right. It's kind of it. Maybe going a little bit to the right is not really an option for it because the mountain is very steep that way. So it can go a little bit to the, left. It cannot go left. It can go a little bit to the right, or it can go down. So every position, it has these two actions. And so it can kind of like, if it goes all the way to the right, then it can kind of go diagonally and approach this corner. And if it's just going somewhere, then the path is going to be something like this. I don't know whether you have seen this really awesome videos of freestyle skiing. There was a recent competition at Kicking Horse. They're beautiful. So people just go up on the mountain, they find a path, they go down, and they are judged based on how many tricks they were doing and so on and so forth. And the competitor with the highest score is going to win. It's very exciting. And so here's our competitor, this little robot, and it has time to practice to find out what is the best way of going down to maximize the score. And it happens that there is a very good trick that it can do if it approaches this corner. So there is here a huge cliff that is not so big that it's going to die, but it's like really big. So it's going to impress the judges a lot if it goes there and jumps down on it. Maybe can do some tricks after it. And there are other small tricks that it can do, but they're kind of like nothing compared to this cliff. So everything, like the most compelling way of going down is going all the way to the right. Climber's right, skier's left. And so initially, this terrain is kind of hidden because it's also in the woods. So you don't see that there's this cliff there. So it really has to go and ski for a couple of days to figure out where to go. Okay? So it needs to figure out the features of the terrain, and it has to do it in some way so that when the day of the competition comes, it can do the best run. So what is the little robot is going to do? What is it going to do if it uses epsilon greedy? So this is a good skier, so it knows how to control itself. It knows if it wants to go left, it will go left. If it wants to go straight down, it's going to go straight down. There's no question about it. What it doesn't know is where are the big rewards. And so in reinforcement learning parlor, of course, you could say cliff, whatnot. This is a big reward here. So you get plus 100. And if you get down here, then you get plus 1. For any of these are not comparable. Here the score is really standing up. Okay, so this is the terrain, and this is the problem that the skier has to solve. So let's think about what epsilon greedy is going to do in this context. All right. If you want to, like, let's make it a little bit more specific, because okay, now it seems it's continuous state space, and like, okay, that's complicated. Let's just think that you have a grid word. Grid words are good for everything, and it's like a 2D thing. So let's discretize the space. So you have maybe an n by n grid word. That's kind of the size of this mountain. And so at every cell of the grid word, there are 2 legal actions, just going down to the next one or going climber's right to the next cell. So these are the 2 actions that you can take. And you know in advance that this is the effect of the 2 actions. So in a way, the dynamics is known ahead of time. What is not known is the reward. So here, if you're arriving at any of these cells, you get a score of plus 1 up to the very end. But if you arrive at the very corner, which is just accessible by taking the diagonal actions all the way, then you get a reward of plus 100. So what is epsilon greedy going to do? Let's say with your favorite algorithm, or like maybe it's speed it up. It could be Q-learning. It could be, I don't know, SARSA or whatnot. But you can also imagine that, OK, without the skier, that here the features are not going to change. So if you see that there is a nice feature, the feature is going to stay there. So it's not like other skiers are going to ruin it for you or something. So if you see that the reward was plus 5 here, then it's going to be plus 5 on the next run as well. And you can just remember that. So what does epsilon greedy does in this case? Well, initially, it doesn't know what to do. Maybe the Q values are all 0 everywhere. So maybe let's think about a model-based solution, like you solve for the optimal plan given what information you collected before, and you like to initialize it 0, right? Like we are not doing initialization high. We can talk about initialization high later, whether that would be a good solution to this case. But let's just, commonly suggested initialize Q-learning with 0 values. So let's just initialize all the rewards at 0. You initialize the rewards at 0, and then you let this thing go. What does it do? It's epsilon greedy. It's with some probability. It's going to deviate from the plan. Initially, what is the plan? It doesn't know anything. So every action looks the same. So adding randomness at that stage, I mean, like maybe it's arbitrary. OK, if it's very clever, then it would say that, oh, if 2 actions look the same, then I randomize between the 2. If you add epsilon greedy on the top of it, so now you're making this super clever algorithm. Like the standard algorithms are not going to do anything like this, right? They're not going to memorize right away. These are the rewards. They're not going to solve for the optimal plan, optimal policy, given what they memorize, and so on and so forth. Q-learning is lazier than that, or SARS is lazy. It's going to be much slower usually. But OK, let's say you have this super algorithm. So if it doesn't know anything, if it doesn't know which action seems to have the highest value, then it flips a coin and chooses at random between the two actions. And you can add an epsilon amount of randomization on top of that. That's not going to do anything if you already decided that the two actions are equally interesting. So initially, what it does is that it randomly chooses actions at every state. So it's going to go down. It's kind of like a random walk that it executes, right? And so in the random walk, if I flip the whole thing, then you can imagine that, okay, so that is done, but maybe I show it this way, and that is climber's right. So that's climber's right, and this is down. And so for every, it's kind of like, this is tilted 45 degrees now, or something like that. And then distorting the geometry a little bit so that we can imagine what this random walk is going to look like, right? So now tilted sideways, this is where the plus 100 reward would be. This is where the plus 1 rewards are. And initially, we don't know what the rewards are. So the initial guesses for the rewards are all 0. You could have intermediate rewards, but they happen to be all zeros anyway. So we're not going to keep that track of those. So this is the reward. This is the belief of the agent about what the rewards are. This is the truth. OK, so initially, agent thinks that, OK, all the rewards are 0. So then it executes a random strategy. It's completely random. And it comes down somewhere on a mountain. So maybe it arrives here. OK, so when it arrives there, it will see that, oh, there's a reward of plus 1 there. OK, so it's going to remember that. There's a reward of plus 1. And it's going to say, OK, so I learned something. That's good. So what happens on the next run for little robot skier? What do you think? Because the rewards that you're receiving, unless you're hitting this very corner, is plus 1 at the very end. That's fine.
Follow the greedy action until we hit epsilon.
Yeah, so what will the greedy action tell us to do? Let's get back to the plus 1, because it was better than the zeros, right? So it's kind of like you have this magneted there, and then, OK, you're occasionally deviating from this magnet. Was there a comment? OK, so what happens is that the next trajectory is going to kind of stay in the vicinity of this, right? It's like you're deviating sometimes. But if you're deviating here, so let's say, OK, so let's get rid of these arrows. So this was trajectory number 1. Let's say you are deviating at one point because you're randomizing. So here you choose, whoa. OK. Here you chose, OK. I guess this is, but I don't have any other colors. All right, OK. So this is the spot where we chose not to go down, but to go this way. So when we are here, if we take a greedy action, which way does it want us to go? Yeah, it's actually like after we learned that there is a plus 1 here, there will be some optimal solutions, kind of like this coming down this way. And if you're deviating from there, you definitely want to get back, right? So now you can have 2 deviations from in a row. You still want to get back. You might not be able to get back completely because you're deviating too much, in which case you discover something in the vicinity of the original discovery. And that's indeed what's most likely to happen. So you're discovering this +1. But the question is, what is the rate at which we are going to go and discover that we shouldn't go actually this way? So now we have 2 +1s. And so that kind of tells us that, okay, like this region, and they are pretty close to each other. So that tells us that this region is pretty good. We should be staying pretty close to it. And so the next run is kind of going the same way. And the result of that is what you have seen, is that you might have some little chance that you're expanding this region, but it's not working very well for you. It's kind of like working very, very slowly. And I can make it even more challenging by, for example, if the rewards were initialized at +1 at all the time, then none of the new runs would give you any new information until you hit the +10, the +100, right? So then everything looks the same all the time, and epsilon greedy is going to fall back to following random trajectories. Okay? And so then the question is, what is the probability that we're going to hit the +100 if we're following random trajectories? How many trajectories are we going to need for that? So let's consider this case. So now I changed that. The initial knowledge is that we have +1s here everywhere. And in this case, nothing new is learned from any of the runs until we hit the +100, which means that in every run, we are following the uniform random strategy. That just means a random trajectory. So what's the probability of hitting, if you have this n by n grid, what's the probability of hitting this very specific value at the end, the very specific corner?
1/2 to the n.
Yeah, that's correct. 1/2 to the n. Why is 1/2 to the n? They are 1/2 probability of going the right way. And you have to do this n times. And each and every time, you have to choose the right direction. So the probability that randomly bumping into the big reward is 1/2 to the power of n. So then the next question is, what do you think? How long does it take, if we follow this strategy, to learn about that there is a reward that's +100? An expectation. Like what's your expectation of, like, how long is it going to take? So it's similar to flipping a coin, right? You're flipping a coin, and the success probability is 1/2 to the n. Yeah. So the inverse of this success probability gives you the average number of coin flips under which you're going to see the first head. So the expected number for hitting +100 for first time. So expected number of runs, the full runs, is going to be 2 to the n. So the total experience that you need to collect to solve this problem is 2 to the n times n. Okay, we don't really care about the n. And trajectory stuff, rough lengths. So that's enormous, right? Like it's a very simple problem. And we see that this strategy can be very, very unlucky. So now we have a few remedies. So there was optimistic initialization. So how would optimistic initialization work here? So you like what does it do? Yeah, I was more interested in the mechanism of it. Like, you're saying what's the benefit? You're saying what's the benefit? I'm asking, how does it work? That's right. So what's the high value that we should be setting the rewards to? Huh? So that would result in some good learning. Anything above 1 is useful here, right? Yes.
Like if you deviate by two states, how would the agent know how to get back to the original state?
In this case, we said that it kind of, it's a good skier, so it knows that it can ski down like this way or that way. So it knows the dynamics of the word. What it doesn't know is the rewards. It's a simpler setting. If it doesn't know the dynamics, it's more complicated. But it's good to start with something simple. Okay, so we could initialize to something like +2, or the terminal rewards, let's say, because we know that the other rewards don't matter. And then optimistic initialization would work by basically eliminating positions, right? So if you bump into a position, then it eliminates it, and then it's going to plan something such that it doesn't repeat the same mistake. So in general, when you have optimism some way, optimistic initialization is an example of that. This is what's happening. You're optimistic about the values. And then if you try something out that you thought has the potential of being good for you, then there are two things that can happen. Either you win, it was good, or you learn that it was not so good. So that's how the mechanism of optimism is really helpful. So you start to eliminate things in a very systematic fashion. And so for this optimistic initialization, how long does it take for it to learn in this case? So let's say we initialize the values, this belief, at all the terminal states to, I don't know, +2. How many runs does our skier need for it to guarantee that it knows where the big reward is? It's maybe a minus. But it's yeah, that's the answer, right? Because once it goes down once, so let's create the new belief. The new belief would be, it's like +2 everywhere. So once it goes down, let's say it came down to here, then it learns that this is only giving you a reward of +1. And everything else looks more attractive. So that's kind of eliminated. So that's kind of the mechanism by which these optimistic algorithms work. They prove them to themselves that something is not good. and then they will not keep on trying to do the same thing. Whereas because they are optimistic, everything else that was not tried still looks good. So once it eliminates that position, then it will choose some plan to get to somewhere else, and it will follow that. If you add a little randomness to it, it might hurt its performance a little bit, but probably not too much. It depends on how much randomization you add. If you add too much randomization, we are back to just the random coin flips, and that would be really bad. So that's how too much randomization is absolutely unhelpful in this setting. So it eliminates one position after every run. So after n-1 runs, at most, it eliminated all the n-1 positions, which are not the most rewarding, so it knows where to go. So that's why the number of runs needed to discover big reward in this example is going to be n-1. Well, it's because like once you ruled out n-1 options, you are left with one option. I mean, like in this example, we know that that's not the worst one. So in this example, we know that you solve the problem after n-1. But okay, so if the problem was slightly more challenging or interesting, then you might need to look at all n different things. You have no guarantee that there will be no revision of your belief, right? Because you had this optimistic initialization. Actually, this initialization is not even optimistic. So that's another discussion point, right? So here, the choice of a reward of +2 just guarantees that we can eliminate the really bad options, all the options that are below +2. And in this example, they happen to be pretty much everything else. But if you're arbitrarily setting some value, then that kind of guarantees that eventually, if there is something that's at least as good as the initialization, you will find that, and you will find it quickly. But if there were a lot of options that were better than this initial value that you were using, so let's say +2, and we had lots of +100s all over the place, then this wouldn't work. So it's kind of crucial that this initialization, you somehow know something about the range of the rewards. It's like really hard to get away in these problems without knowing something about the range of the rewards. Yeah, right. So that would be, yeah, I think that if you have no idea about the range of the rewards, then you could set the values to infinity. In this case, we are kind of really trusting the values that we are seeing. So there is no incremental update of the rewards. There is no expectation that the rewards are going to be noisy, and therefore we should be updating values in a slow fashion, like, you know, sample averages or something like that. So therefore, this plus infinity initialization is fine. But if the problem was noisy, then we would be in trouble with that, right? So you try to do an incremental update with plus infinity, the initial value. What's the updated value? Still plus infinity. That's not really good.
Like initially +infinity, but then after you sort it, just get rid of it.
Yeah, if you only see it once, then you can be very unlucky. So imagine that I make these rewards noisy now. So it's like a normally distributed reward with this mean and some variance. And then if I get unlucky with this, then I'm dead again. So it's really challenging to do anything meaningful unless you know something about the scale of the rewards. So people are trying really hard to develop algorithms which are completely scale-free of rewards, but I think it just, yeah, not sure how good those algorithms can be for the full reinforcement learning problem. I guess if we are in a bandit, so this is also very similar to a bandit with kind of just many arms, except that it's kind of like structured, right? Because if you can have multiple paths that leads to the same point. So those are maybe 2 arms. And you would need to know that, okay, if they lead to the same point, then they will have the same payoff. So if you are in a bandit problem anyways, then if you don't need to know necessarily the scale of the rewards. If you think about, for example, what UCB is going to do, UCB doesn't need to know the scale of the rewards. It's going to try everything. Maybe you initialize, I mean, initially, it has this strategy that whatever it didn't try still has to try. With that strategy, if you look at all the possible paths, there are too many of them, you would be in trouble. So you would need to be more clever. But okay, so if it's a small bandit problem, like you only have a few number of actions or a few arms, then you try all of them. That was effectively the same thing as like starting with plus infinity. And after that, you just update your statistics, you create this confidence intervals, and you go with the upper confidence values. To create the confidence intervals, you need to know one more thing, which is kind of like how big is the variance, or like how variability, like what's the variability of the rewards are. If you don't even have any such information, there are ways of doing things still. So, but things are becoming a little bit more hairy. Anyways, for reinforcement learning, most of the time people just assume that the rewards are between 0 and 1. Is that assumption reasonable? If you're in an application, you don't even know the range of the rewards, I think you're in a deep trouble. I can, like, people do this, right? So one of the popular benchmark suite is this Atari benchmark suite of like, there are like 56 computer games from the 80s developed for an old console. And people try to train reinforcement learning algorithms to play all those games. And they have rewards everywhere, like across different scales. And the algorithms are usually not taught ahead of time what the scale of the rewards are. And that creates, I think, a lot of trouble. If you like, more realistically, if you're in an application, we'll have, I think, some idea about the scale of the rewards, and then you can use that. Anyways, so this tells you a little bit about how optimism helps you. The optimistic algorithms, the full-blown optimistic algorithms, they are very similar to UCB. They build confidence intervals for the transition probabilities and for the rewards. And once they have the confidence intervals for the transition probabilities and the rewards, they solve this optimistic planning problem. In the optimistic planning problem, like, for example, you have this episodic finite horizon setup, you would think about the highest possible rewards that you can get at every position and the probability distributions that best support of getting to, within your confidence set, that best support of getting to the highest possible reward. So you can develop some computationally efficient algorithms around these ideas. They are like dynamic programming, but you not only have one reward function and one transition probability, but you have a set of them. but the sets have nice structure, and you always try to get the best possible value. And you can run this efficiently, and you would get much better performance. And they are quite general. The algorithm that you saw in the video is kind of working along the same lines. It has many other moving parts and like neural networks and whatnot, but it is based on these ideas of optimism as well. All right. Wow, I'm finishing early today. So yeah, so we can have lots of questions today. Yeah. You can be lucky with a problem where the reward structure is such that maybe you don't even need epsilon greedy because the rewards are just leading to a solution. So people indeed are trying to help themselves because many times it's more complicated to implement a clever exploration strategy, and they just want to resort to epsilon greedy, and then they discover that, oh, hey, it doesn't work. But then they start to manipulate the reward structure. They give it a fancy name. They call it reward shaping, and they try to help themselves that way. Yes.
Epsilon greedy like only works if like the rewards are like in nearby states, right? The rewards like group together.
Yeah, so you can imagine that if you like initially what we described is that you discover these plus ones here, and then there were all zeros everywhere. But when you're deviating a little bit, there would be a gradient towards the plus 100. So if the rewards would be such that there is some directionality there, then epsilon greedy can have a chance, right? So if the next one, you discover both sides of plus 1, here you see that you have 0, maybe -1. Here you start to see a 2 and a 3 and a 4. Then it will push the trajectories up. It's not going to be very clever of saying that, oh, I extrapolate and then I need to go there. But it's just like little by little, it can get to the goal. So if you have such a gradient, epsilon greedy is great. But that required kind of a little bit of luck with the choice of the reward function, right? But of course, people are running all these experiments, and a lot of times you just see people use epsilon greedy, and a lot of problems, it seems to be doing fine. And that's because the reward structure is not as adversarial as here. So here it's chosen to make a point. But at the same time, it's a little bit unsatisfactory, I would say, that you find a very simple example. And on that very simple example, the well-designed algorithm gets the solution in logarithmic time of the time needed to get a solution with epsilon greedy. So epsilon greedy is exponentially more expensive in some of the examples. And when was the last time that we, as in computer science, wouldn't have been worried about if you have an exponential blow up of something, right? Like, so I kind of feel that just, yeah, it seems not quite prudent to say that just because we have seen a bunch of environments where epsilon greedy is doing fine, to think that it's always going to be fine. And lo and behold, people time to time bump into problems where it's absolutely not fine. And you have to work much, much harder to get reinforcement learning off the ground. So I think that, yeah, I hope that in the long run, people are going to give up on epsilon greedy, and they will go and implement the clever exploration techniques, because I think that it just almost like a shame that we are still doing this, despite that we know it very well, that this is just a bad idea. All right. Okay. I don't know. Any other questions, comments? Yeah. Well, we will get to function approximation, and then we're going to talk about follow-ups to how to do clever exploration in, like the CMPUT example I was showing you. It's not discretized; it's continuous. Yeah, that's going to be the most exciting part, I hope. I mean, like, okay, we are learning a lot in this course, so it's like I realize that there is so much. So we're not going to do any imitation learning. But we can chat about imitation learning. I have pretty strong opinions about that too. Huh? What?
What's your opinion?
Well, no, I'm just think about these exploration problems. So imitation learning is like running epsilon greedy and then hoping that it's going to get you the right data. I mean, it's okay. Like if you want to establish a baseline, you collected some data. Yeah, try to do it. But even that is quite questionable a lot of times. If you have a stochastic environment, it's going to deviate from the data. And then when you're deviating from the data and you are relying on somehow just generalizing based on the data to what actions to take, it's kind of a big leap of faith. Yeah.
Isn't like Tesla, like autopilot,
Yeah. Things. Well, we have seen a few videos of how those cars are crashing.
Okay.
So I probably wouldn't want to rely on autopilot. I'm like, I would test it. It would be fun, but getting like it freaks me out actually because I know that I'm the lazy person. So maybe in the wrong run, it's a human nature because it doesn't tend to make mistakes. You would start to trust it, and then you would forget that it's just like it can be huge holes can be in that controller. Exactly because of this, the way it's set up. Yeah.
What do you think's a better solution?
Yeah, I mean, like, so the way people are building airplanes is, I think, a better solution. And controllers for airplanes, they are landing most of the time, they don't crash. There is no guesswork there. There is no reliance on proven components. So you just build component by component and then prove yourself that it's gonna work. I think we should, like, it's not clear whether this is how people are going to build it, but because there is this other effect that people are very good at just starting to trust things. And, if statistically speaking, it's kind of working, then it's kind of like, All right, okay. See you.